Imagine standing beside two massive steel plates, each several inches thick and weighing thousands of pounds. Normally, joining metal of that size would require multiple welding passes, countless hours of work, and a tremendous amount of skill. But what if there was a welding process capable of joining those giant steel sections in just a single pass? A process so powerful that it can weld steel up to 300 millimeters thick while slowly climbing upward like molten metal defying gravity itself. Sounds impossible? Welcome to the fascinating world of electroslag welding, better known as ESW. Unlike most welding methods that rely on a visible electric arc throughout the process, electroslag welding does something surprisingly different. It starts with an arc, but then the arc disappears, yet the welding continues. In fact, once the process gets going, molten slag becomes the real source of heat, generating temperatures high enough to melt steel and create incredibly deep welds. That's one reason ESW became a game-changing technology for shipbuilding, heavy machinery, storage tanks, bridge construction, and other industries where enormous steel structures are built every day. But how exactly does electroslag welding work? Why is molten slag more important than the arc itself? What equipment makes this unusual welding process possible? And why do engineers choose ESW when working with some of the thickest steel sections on Earth? Stay with us because by the end of this video, you'll understand how a pool of molten slag can accomplish something that would take many other welding methods hours or even days to achieve. Let's get started. What is electroslag welding? Electroslag welding, commonly abbreviated as ESW, is a specialized welding process designed primarily for joining very thick metal sections in a single pass. It is classified as a high-productivity welding method and is usually performed in a vertical or near-vertical position. What makes ESW unique is that it combines characteristics of both arc welding and resistance welding. Initially, an electric arc is used to start the process. However, once sufficient molten slag has formed, the arc is extinguished. From that point forward, electrical current passes through the conductive molten slag, generating heat through electrical resistance. That heat melts both the filler metal and the edges of the workpieces being joined. As the molten metal solidifies behind the welding zone, a strong welded joint is formed. That allows incredibly thick materials, sometimes ranging from 25 millimeters to 300 millimeters, to be joined in a single welding pass. That's something very few welding processes can accomplish.
Why was electroslag welding developed? To appreciate the importance of ESW, consider the challenges of welding thick steel sections using conventional methods. Processes like shielded metal arc welding, or MIG welding, often require multiple weld passes, extensive joint preparation, significant labor, and long production times. For extremely thick steel plates, these requirements can become expensive and inefficient. Engineers needed a faster solution. Electroslag welding was developed to address these challenges by creating a process capable of depositing large amounts of weld metal rapidly while maintaining deep penetration. The result was a welding method that dramatically reduced production time in heavy fabrication industries. Where is electroslag welding used? Electroslag welding is not typically found in small workshops or hobby garages. Instead, it is primarily used in industries where massive steel structures are fabricated. Let's look at some common applications. Heavy industrial construction. One of the most common applications of ESW is joining thick steel plates used in industrial structures. When steel sections exceed the capabilities of conventional welding methods, ESW becomes the preferred solution. Its ability to create a complete weld in a single pass saves enormous amounts of time. Shipbuilding. Modern ships contain large steel components that require strong and reliable welds. Electroslag welding is often used when assembling thick sections of hull structures and other major ship components. The process helps shipbuilders improve productivity while maintaining structural integrity. Storage tanks. Large storage tanks used for oil, gas, chemicals, and water often require thick steel walls. ESW provides an efficient way to join these heavy sections while reducing overall fabrication time. Thick-walled pipelines. Certain industrial pipelines feature thick walls that must withstand high pressures. Electroslag welding is capable of producing deep welds suitable for these demanding applications. Structural steel fabrication. Heavy bridges, large buildings, power plants, and industrial facilities frequently utilize thick structural steel sections. When proper procedures are followed, ESW can be an effective solution for joining these materials.
Aluminum bus bars. Beyond steel applications, electroslag welding is also used for joining large cross-sectional aluminum bus bars used in electrical systems. Understanding the major components of an electroslag welding system. To understand how ESW works, we need to examine the equipment involved. Each component plays an important role in maintaining the process. 1. Power source. Every welding process requires energy. In ESW, a power source provides the electrical current needed to generate heat. However, unlike traditional arc welding, most of the heat is eventually generated through electrical resistance within the molten slag. The power source continuously supplies energy as the welding operation progresses upward. 2. Filler metal. Filler metal provides the material needed to fill the joint between the workpieces. As welding progresses, the filler metal melts and becomes part of the finished weld. Because ESW deposits large amounts of weld metal, the filler wire feed system must operate continuously and reliably. 3. Flux. Flux is one of the most critical elements of electroslag welding. At the beginning of the process, the arc melts the granular flux. As the flux melts, it forms molten slag. This slag serves several important functions. It 1. Generates heat through electrical resistance. 2. Protects the weld from atmospheric contamination. 3. Covers the molten weld pool. 4. Helps maintain proper welding conditions. Without the slag layer, electroslag welding simply wouldn't work. 4. Wire feeder. The wire feeder continuously supplies filler wire into the molten slag bath. As the wire enters the heated zone, it melts and contributes to the formation of the weld. A steady wire feed is essential for maintaining consistent weld quality. 5. Welding head. The welding head controls the movement and positioning of the electrode. As the weld progresses upward, the welding head moves accordingly. This ensures the process remains stable throughout the operation. 6. Guide tube. The guide tube directs the filler wire into the welding zone. It also helps protect portions of the electrode from excessive exposure to the molten slag. This improves process stability and efficiency. 7. Retaining blocks. One of the most interesting components in ESW is the retaining block. Since the process involves a large volume of molten metal and slag, something must hold everything in place. Retaining blocks act as temporary molds. They contain the molten metal and slag within the joint until solidification occurs. Without them, the molten material would simply flow out of the joint.
How does electroslag welding work? Now let's examine the actual welding process step by step. This is where electroslag welding becomes truly fascinating. Step 1. Preparing the joint. The process begins with two thick metal plates positioned vertically. A gap is left between them where the weld will be formed. Retaining blocks are placed on both sides of the joint to contain the molten materials. The welding equipment is then positioned at the bottom of the joint. Step 2. Arc initiation. Unlike what many people assume, electroslag welding does start with an electric arc. The electrode contacts the workpiece, generating heat. This heat begins melting the granular flux placed in the joint area. As the flux melts, it transforms into molten slag. Step 3. Formation of the molten slag bath. As more flux melts, a pool of molten slag develops. This molten slag becomes electrically conductive. At this stage, something remarkable happens. The slag bath becomes large enough to extinguish the arc, and surprisingly, that's exactly what the process is designed to do. Step 4. Resistance heating takes over. Once the arc disappears, electrical current continues flowing through the molten slag. Because the slag has electrical resistance, it generates tremendous heat. This is similar to how an electric heater works. Instead of relying on an arc, the process now relies on resistance heating. The molten slag becomes the primary heat source. Step 5. Melting the filler metal. As the filler wire enters the molten slag, it melts rapidly. The molten metal accumulates at the bottom of the slag bath. At the same time, the heat melts the edges of the base metal plates. This allows both materials to fuse together. Step 6. Weld formation. As additional filler metal is deposited, the molten weld pool gradually rises upward. The retaining blocks keep everything contained. Behind the molten zone, the metal cools and solidifies. A strong weld is formed as the process progresses vertically.
Step 7. Continuous upward movement. One of the defining characteristics of ESW is its continuous upward movement. The welding head, guide tube, and slag bath gradually move upward together. The process continues until the entire joint is completed. Remarkably, even extremely thick sections can often be welded in a single pass. Why is electroslag welding so productive? The answer comes down to deposition rate. Electroslag welding can deposit large quantities of filler metal much faster than many traditional welding methods. Instead of performing multiple passes, operators often complete the entire weld in one operation. This dramatically reduces welding time, labor costs, joint preparation requirements, and production delays. For large industrial projects, these savings can be substantial. Limitations of electroslag welding. Despite its impressive capabilities, ESW isn't suitable for every application. Several limitations must be considered. Position restrictions. Electroslag welding can only be performed vertically or near vertically. The process depends on gravity and containment systems to maintain the slag bath. Flat or overhead welding is not practical. Thickness requirements. ESW is intended for thick materials. It generally becomes practical only when materials exceed approximately 19 millimeters in thickness. For thinner sections, other welding methods are usually more economical. Material restrictions. Although ESW can weld several materials, it is most commonly used on mild steel and low alloy steel. Special procedures may be required for other materials. Advantages of electroslag welding. Now, let's look at the benefits that make ESW valuable in heavy fabrication. Extremely high productivity. Perhaps the biggest advantage is speed. The ability to weld thick sections in a single pass significantly increases production efficiency. High deposition rates. Large amounts of filler metal can be deposited quickly. This makes ESW one of the most productive welding methods available. Deep penetration. The process provides excellent penetration into thick materials. Strong joints can be achieved without extensive edge preparation.
Reduce distortion. Because the weld is completed in one continuous pass, distortion is often lower than with multiple pass welding methods. Lower joint preparation costs. Compared to conventional welding processes, ESW typically requires less extensive joint preparation. This reduces fabrication costs. Semi-automatic operation. Automation improves consistency and reduces operator workload. This contributes to higher overall productivity. Disadvantages of electroslag welding. While ESW offers impressive advantages, it also has drawbacks. Coarse grain structure. One of the biggest concerns is the development of a coarse grain structure within the weld. This can negatively affect toughness. Slow cooling rate. Because large volumes of molten metal are involved, cooling occurs relatively slowly. Additional cooling measures may sometimes be required. High heat input. The process introduces substantial heat into the base metal. This can affect material properties and may require careful control. Limited welding positions. Only vertical or near vertical welding is possible. This limits flexibility compared to other welding processes. Higher initial equipment costs. Electroslag welding equipment is generally more expensive than conventional welding setups. The initial investment can be significant. Conclusion. So how does electroslag welding work? It begins with an arc, but unlike conventional welding processes, the arc's job is only to get things started. Once molten slag forms, electrical resistance within that slag becomes the primary source of heat. The molten slag melts both the filler metal and the edges of the workpieces, creating a powerful single-pass welding process capable of joining some of the thickest metal sections used in industry. From shipbuilding and structural steel fabrication to storage tanks and heavy industrial equipment, electroslag welding has transformed the way massive steel components are joined. Its extraordinary productivity, deep penetration, and ability to weld thick materials in a single pass make it one of the most impressive welding technologies ever developed. While it has limitations, especially regarding welding position and material thickness, its advantages continue to make it an essential process in heavy manufacturing around the world. And the next time you see a giant steel structure towering above a construction site or a massive ship crossing the ocean, remember, there's a good chance electroslag welding helped hold it together. If you enjoyed this video, don't forget to like, subscribe, and turn on notifications for more deep dives into welding technology, metal fabrication, and industrial engineering. Thanks for watching, and we'll see you in the next video.